Hi everyone. Today we're going to be looking at transformations of functions, particularly the transformation rules. To begin, let's consider the parent function y equals f of x and its table of values. Below, I want to graph each of the following transformations by first creating a table of values and then describing the transformation from the parent function. So let's first consider operations that affect the output. So looking at this here, we have 2 times f of x. So if I were to construct a table of values, we would have x, 2f of x. All of our x values are the same. So we have -3, -2, 0, 1, and 2. But then all of our function outputs are going to be doubled. So 3, 0 is still 3, 0. -2, 1 becomes -2, 2. 0, 0 is still 0, 0. 1, -3 becomes 1, -6. And then 2, 0 is still 2, 0. So all of our function outputs are doubled from the parent function. If we were to graph this, we have -3, 0, -2, 2, 0, 0, 1, -6, which is off the grid, which is okay, just kind of approximate. And then another x-intercept, 2, 0. So sketching in this graph here, we've got a similar function, but it's more like elongated or stretched out. For b, here we have f of x minus 2. So let's make our table of values. We have f of x and then minus 2. So we're taking all of our function outputs and we're subtracting 2. All of our inputs, again, are unchanged. So we have -3, -2, 0, 1, and 2. But then all of our function outputs, we subtract 2. So instead of -3, 0, we have -3, -2. Instead of -2, 1, we have -2, -1. Instead of 0, 0, we have 0, -2. We have 1, -5, and then 2, -2. So let's go ahead and graph this. -3, -2 is right here. -2, -1, 0, -2, 1, -5 is kind of off the grid, and then 2, -2. Okay. And then for C, here we have -f of x. So we have our table of values, x, -f of x. So we're taking all of our function outputs and we're flipping the sign. We're making it negative when it's positive, and we're making it positive when it's negative. So our function inputs are still the same, -3, -2, 0, 1, and 2. But then we have, instead of -3, 0, we still have -3, 0. Instead of -2, +1, we have -2, -1. We have 0, 0, 1, +3, and then 2, 0. So graphing this, -3, 0, -2, -1, 0, 0, 1, 3, and then 2, 0. Okay. So now let's take a look at these graphs and see if we can come up with a description of the transformation. For letter A, we've got this graph and it's stretched vertically. So this is a vertical stretch by a factor of 2. And remember, that's where we doubled all of the function outputs. For letter B, we have the same exact graph, but then it's just shifted down 2 units. So we have a vertical shift down 2 units. And last but not least, a negative out in front. We have the exact same graph, but it's like mirrored over the x-axis. This is reflected, or a reflection, over the x-axis. Okay? All right. Now let's take a look at operations that affect the input. Now we're going to have to get a little bit creative with our table of values. So remember, our parent function had inputs -3, -2, 0, 1, and 2. Now we have to consider what inputs would lead us to those original inputs. So looking at this table, we have x and f of 2x. We're looking at the input. So what x value do I need to double to get to -3? The answer is -3 halves. If I double -3 halves, then I land on 3. For -2, what number do I have to double to get to -2? The answer is -1. 0 stays the same. And then we have 1. So what number do I have to double to get to 1 is 1/2. And then what number do I double to get to 2 is 1. So these are our new function inputs. All of our outputs are still the same. There's no other transformations to the output, so we still have the function outputs 0, 1, 0, -3, and 0. So let's go ahead and graph this. -3/2 0 is like -1 and 1/2, 0. -1, 1, 0, 0. 1/2, -3, and then 1, 0. So we've got a similar function. Notice all the function outputs are the same. For letter B, f of x minus 2, so x, f of x minus 2. So again, we're going to have to look at the function inputs. Instead of -3, -2, 0, 1, and 2, we're going to say what number subtracted by 2 gives us each of those values. So what number minus 2 gives us -3? The answer is -1. What number minus 2 gives us -2? The answer is 0. What number minus 2 gives us 0? The answer is 2. And then our other inputs, 3 and 4. All of our function outputs, again, remain the same. So we have 0, 1, 0, -3, and 0. So now we have the graph here. We have -1, 0, 0, 1, 2, 0, 3, -3, and 4, 0. Okay, and last but not least, we have x, f of -x. Okay, so here we're looking at what value, if I make it negative, gives us those 5 original values. So to get -3, we're going to choose +3. To get -2, we choose +2. We have 0, -1, and then -2. Function outputs, again, are still the same. 0, 1, 0, -3, and 0. Let's go ahead and plot those. We have 3, 0, 2, 1, 0, 0, -1, -3, and -2, 0. Okay, so now let's look at these graphs and see exactly what do we notice about these transformations and their original equations, or representations, I should say. So for the first one, here we have a compression, horizontal compression, by a factor of 1/2. So a horizontal compression by a factor of 1/2. If I put a coefficient in front of the input, if that coefficient is greater than 1, it's going to be a horizontal compression by a factor of its reciprocal. Okay. For letter B, here we have all of those same values. The graph looks identical, but everything is shifted to the right 2 units. So here we have a horizontal shift right 2 units. And last but not least, putting a negative in front of the input is a reflection over the y-axis. Okay? So in summary, operations that affect the output will affect the graph vertically. So a vertical stretch, shift, or reflection over the x-axis. And operations that affect the input will affect the graph horizontally. So that could be a stretch or compression, a shift, or a reflection over the y-axis. Okay? We're going to get a lot of practice on this in class, so we'll see you tomorrow. Have a great day, everybody. Goodbye.